Okay, it is time to begin Unit 11B, which is pressure measurement, and then we'll talk about buoyancy forces and Archimedes principle. We begin with pressure measurement. There's two shown on this particular slide. One is what you probably heard of before, barometer, which measures barometric pressure, and it has one side open here and the other side is closed, and this is vacuum in there. And so you have a height difference between the side with vacuum with no pressure and the side with the pressure is being measured. And that height gives you a measure of the pressure. Now, nowadays is much better ways of measuring pressure than this, but this is how people used to do it. And they used to do it with a tube full of mercury usually. And so 1 unit of pressure is actually millimeters of mercury, where you measure H in millimeters and mercury is that liquid. And you can probably figure out how this works, right? What's pressure versus depth? You know that if the height over here, this height in the fluid has the same pressure as right over here, because it's the same height. We talked about that before. And so the weight of this much fluid above it with no atmosphere is equal to the pressure on this side. So we know that rho of this fluid, say rho mercury times our favorite G times this height is equal to the pressure over here. And you probably all heard of, what's the pressure? It's like, 29 point something or maybe 30 millimeters of mercury. Well, that because rho G times that number of millimeters gives you the H, or gives you the atmospheric pressure that day, and the H is how many millimeters of mercury you have. That's a unit. On the other side, it's actually very similar, except you've got a tank over there that's either a reference tank with a reference pressure in it that you want to measure against, or you're trying to measure the pressure in there, and so you, and it's changing, so you just hook it up as a link to a manometer and compare it to atmosphere on the other side. And if they're level, it's equal to atmosphere, and if it's not, you can measure. So take a look at that. Is the tank pressure there lower or higher than atmosphere? It's lower. How do you know? Because it's pulling the, well, we say it's apparently pulling up the fluid on that side. What does that mean? It's getting rho GH to balance the pressure on the two sides, because from the pressure on the left, the open end of the manometer, is rho GH less than the pressure on the tank, right? That's why it goes up. If H is negative, then it'd be rho GS more in the tank. Push it up on the other side. So this can measure either pressures higher or lower than the atmosphere or the reference on the other side. And that was another common way to measure pressures. And and there's your gauge pressure and the absolute pressure, because you have vacuum on the other side. Okay, so now we go on to a tank problem, and to do this, we'll hop back to our get something placed in here where it needs to be. And yes, we get back to our screen over, here's our screen. And there we are, and I'll even straighten it up so you can see it. That is the problem that should look familiar from what we were just doing, except now we can point at things and write all over it. I seem to have lost one of my pens, but that's okay. We'll just have to do without that color for a little while. Okay, so a manometer, okay, so that's measuring gauge pressure usually, and so that's gauge pressure, so they kind of tie together, Good. It's filled with mercury. What do you know? So the density here, that's just going to come into the row of this stuff in here. And connected to a tank of unknown pressure. The mercury in the manometer is displaced by 200 millimeters as shown. What is the gauge pressure in the tank, including its sign? Well, first we can get the sign. Is the pressure either lower or higher? It's pulling the mercury up, so it's lower. Actually, I'll put pulls in quotes. It pulls the mercury up. Mercury is Hg if you're a chemist. And of course it can't pull. So really, P atmosphere pushes harder from the other side. Because it can't pull. Pressure can't pull. That's what we learned before. So really the way to think about this is the atmospheric pressure is pushing down harder than this pressure, so the atmosphere wins until you get enough weight of mercury that it won't. So the other thing we know is that the pressure is the same. At the same height. Above the Earth. And so really it's this side we're thinking about. And so this is our H. And we have that the P over this, now if we work in this is P atmosphere in absolute, or P gauge equals 0 on this side, so that's what it is down here. And so up here, it's P tank. So P tank is equal to tank, and the gauge pressure is equal to just rho GH minus 0, basically, because that's what it is on the other side in the gauge units. And so and we know that it's negative because it's lower. So maybe that's a better way to put it, because we know it's lower than the atmosphere, so it's going to be negative. Okay, so the plug in the numbers, minus 13,600 kilograms per meter cubed, which is, about 13.6 times higher than water. That's why you use this, because that means this height column is 13.6 times shorter than if it was water. If it was water, it'd be 13.6 times. It's 0.2 meters. So you get 26 times 0.1 for meters. So it's like 2.6 meters this would be if it was water. That's a little bit inconvenient to work with things that big. There's our little g, and h is 0.2 meters. And if you multiply these all out, you end up with something in pascals, right? And this is about 10, that goes about 2, so it's around 26,000, and that's around 2.67 by 10 to the 4. And so this goes to this one. And you check your answer. It's negative because it's lower than atmosphere, and it's the rho GH is the value for the difference there. Okay, so now we look at a barometer, and a barometer is filled with mercury and used to measure the ambient pressure. The ambient pressure is 1 atmosphere. What is the height of the column of mercury? Right, and so we use the same thing as across this whole line is P atmosphere, and the pressure in here is vacuum. So P absolute is equal to 0. P gauge is equal to minus P atmosphere. We're going to be using this one because why not? And so the this here, P here, the absolute, is equal to P at the top plus, on the absolute scale, plus rho GH, and P at the top was equal to 0. And so this is simply rho GH. And you can, okay, this is, by the way, the same height, same pressure principle again. And this is open, so it's the, I mean, this is from here to here, it's the weight of this part of the atmosphere, which is completely negligible. And this here is open, so the pressure here, same as outside the tube, at the same height, of course. And okay, so and this over here is P atmosphere. Okay, so rho GH, again, we plug in the numbers. It's 13,600 kilograms per meters cubed. The pressure here is 1 atmosphere, and you might ask the question, okay, what is 1 atmosphere? Well, we had that before, and if I do a quick look back to what it is, it's 1.013 times 10 to the 5 pascals times 9.8 meters per second squared times h. So we divide both sides by these. They multiply, well, this is divided by those two, and we get h. And h from that turns out to be 760 millimeters. So 760 millimeters is just about 3/4 of a meter. Now remember water, it would be 13.6 times higher. So you're something like 10 meters high if you measure atmospheric pressure with water. And 10 meters, you know, that's 30 feet. That's like the height of your house. So it's inconvenient, let's say, to have something that big, although people used to do it on occasion. But it also tells you, though, something very practical. Suppose you want atmospheric pressure to push water up into a pump. So you've got a pump over here, and the pump replaces the closed end, and you're pumping as much as you can. And suppose you can pump all the way down to vacuum over here. How far can you pull water up to get into the pump? Well, you pull it up about 10 meters, about 30 feet. If it's further than that, you can't get water all the way up, and you have to actually pour water down, what's called priming the pump, to pull it up. And if you can't get all the way down to zero pressure up here to real vacuum with your pump to get it started, then you have to prime it first, even if it's lower, by pouring water into it to fill this with water. Once you get water, then the water holds itself together enough to pull higher than 30 feet. But to get it going is when that really matters, which is why if you have a Cartesian well, and if you live in the country, and it's from deeper than 30 feet, you got to have the pump on the bottom, and you push it up. Remember, you can push with pressure, you can't pull. You only pull it up till it's atmosphere, right? When it's not really pulling, again, it's letting the atmosphere push down against you, and the atmosphere is winning. But if you put a pump down at the bottom, of course, you can push up as high as you want to, which is how you get water up to the top of these buildings. And of course, that's limited by how hard your pump can push water. And some pumps can't push it more than about, say, 10 stories, in which case, building tall than 10 stories, you can't fight with fire that's pumped up by a pump from the bottom. You either have to have a second pump up on the top to pump it further, or you're in trouble. And that's part of the problem that happened in that tragic block building fire in London a few years ago. Couldn't get the water up as high as they needed it to. And so you're supposed to store water at the top, so like in St. Marco Hotel, where it builds up on the way down because you actually have a tank on top of the building, so you don't have to pull it up. Okay, so that is this, and we're going to switch now back to our PowerPoint presentation. And we're going to pop down a few here. So we already did this one. And now let's talk about buoyant forces and Archimedes' principle. So let's first say, what is a buoyant force? It's an upward force, a net upward force, that applies, a fluid applies to an object when it's in the gravitational field, right? So if I throw an object into water, there's a force that the water pushing out. And essentially, you displace some water, and the water isn't like that, so it tries to fill back in, but it can only do it up to its weight in that volume, and that's what the buoyant force is. And Archimedes realized this. He was a Greek who lived in Syracuse, which is on Sicily, which is in Italy, actually. But he was the one that looked at the buoyant force and determined these properties of it. So the magnitude of the buoyant force is the density of the fluid, not the object, but the fluid, times the volume of the displaced fluid, which, if you sink all the way in, is the volume of the object. If you don't sink all the way in, it's just the part of the object volume that's displaced. And g is our gravitational acceleration. So this is key in terms of what is the magnitude of the buoyant force. And the direction is opposite the gravity. So in other words, it's up. Or sometimes it's the apparent gravity force, right? If you have an acceleration, back to the old elevator problem, it's the apparent gravity force that it's opposite. And I'll have a question about that, just to make sure you get it qualitatively right, coming up in maybe about 5 or 10 minutes. Okay, consequence of this is that object will float if the buoyant force is equal to the object's weight, which can only happen, by the way, if the density of the object is less than the density of the fluid. Otherwise, it sinks before this ever happens. The object will rise if the buoyant force is greater than the object's rate. This is how a fish maintains its height. It's got what's called an air bladder. If it expands its air bladder, it is essentially making itself less dense on average. It's changing its density. It can go up and go down. And it will sink if I'll have a demonstration of that coming up too. and it'll sink if the boiling force is less than the object's weight. So another consequence, well, I've said this, is that the density determines whether something floats or not. And before we go on here, that comes later, I want to bring us some demonstrations of these words I was just talking about when it floats and when it doesn't float. And we'll begin with another video here, which I believe is this one. Okay, so which one do we want? This one we want. So there's our friend. If you've ever had to change classes and deal with Keith Warren, that's him.
Wave submerged block. So we see this block weighs approximately 8.5 newtons.
We're going to call that 8.5 newtons, and it's not in the water yet.
The volume of the water displaced will have a particular weight, which equals the buoyant force on the block. And we can see that on the scale.
And so if you look,
the scale drops to 4 to 4.5 newtons. Therefore, we see that we have a buoyant force.
Yeah, now if you look at that block, see how it looks a lot like a brick? Well, that's how we're going to model it. We're going to model it as a brick. And so, well, we're going to see if it's a brick. And how we're going to see is we're going to calculate both the volume of it, see if it's reasonable, and the density of it, see if it agrees with the density of what bricks is supposed to be. Now, you might consider, how can we get two things, the volume and the density of the brick? And the reason for that is really quite evident. It's that you have go out of focus. It's that you have you're measuring two things. So here we have brick in and out of water. There we go. And so we measure two things. The submerged weight and the weight in air, or the apparent weight. Why don't we just say the force to hold it up, because it's an apparent weight. Force to hold it up in air, which is the apparent weight. And that, actually this is the real weight, that's 8.5 newtons. And the force to hold it up in water, and that was 4.5 newtons. So we measured two things, should be able to get two things. And the things we're going to try to get is the volume and density of the object, which looks like a brick. Okay, so let's start. Remember that we're talking about forces, no motion, and that tells us it's a static, no time given, no specific time, initial or final. So that's static, Newton's second law. So think about F equals ma net, and a is equal to 0. So we draw the free body diagrams. So in air, these are the free body or force diagrams. And in the water. So in air, we have, if our little block. It has, oops, that's a little long, doesn't matter too much. Tension going up in that little string we're holding, and going down is the weight. And in water, we have the tension that's going up, it's weaker. We also have the force buoyant going up, and we have the weight going down. Now, these two weights are real weights. mg, mass. It's not apparent, it's the real weight. Weight has a t in it. So let's do Newton's second law on these things here. This tells us that the F net equals T minus W is equal to MA is equal to 0, so T is equal to W. And this is T air, and this is T water, because it's different. The weights are the same, buoyancy is given, but the T's differ. And over here we have F net equals T water plus F buoyancy minus weight is equal to MA is equal to 0. And so we have that the weight is equal to T water plus FB. Well, since these two are equals, by this, then we know that TA is equal to T water plus force buoyancy. Or T in air minus T in water is equal to force buoyancy. And what is the buoyant force? It's the density of water times the volume of the object, because the whole volume of the object, it's the whole volume, since it's submersed, times little g, right? And so I can get the volume directly from this, right? Volume is equal to the T air minus T water over rho water G, which is 8.5 minus 4.5. I can write it out, 8.5 minus 4.5. That's 4 newtons divided by 1,000 kilograms per meter cubed, 9.8 meters per second squared. And if you grind that through to the volume, you get equal to 4.1 times 10 to the minus 4 meter cubed, which is 410 centimeters cubed, which is equal to 0.41 liters. Because liters is a cubic decimeter, right? So it's halfway in between that and that. So you know what a liter bottle looks like, a little less than half that. Does that look about right for that size block? That looks about right. And this one you can say, okay, it's 4 by 10 by 10 centimeters. That's about right too. Sort of square and a little shorter the other way. So whichever way you think about it, it looks about right. Now, so that's the volume. Now let's think about the density. All right, so we go back to this case here. And the weight, okay, TA is equal to rho object times V of the object, which is the same whole V, whole volume, again, times G. And so I can get the density of the object is equal to TA over VG. I put in the numbers, right? It's 8.5 over 4.1 E minus 4 in meters cubed times, that's newtons, and G is 9.8 meters per second squared. And of course the meters, this is Newton meters per second squared, the meters per second squared go out, you get kilograms per meter cubed, which is what you want for density. Anyway, you get 2150 kilograms per meter cubed. And to compare, rho density of brick, I looked it up, is 1922 kilograms per meter cubed. Looks good, because the accuracy we're doing at this, especially that 8.5 reading, looked a little lower than that. So this would be a little lower, it's closer to that. So it looks okay. It's probably brick. And so we could use a little bit better measurement of the forces and get these numbers right on, but we're doing pretty well as it is, right? So that's how you use these things quantitatively. Another way that you can use them quantitatively is to say, what does it mean to float? And what does it mean to float is that the force buoyancy is greater than the weight. That's what it means to float. And so the force buoyancy, of course, is rho fluid times volume of the object times the G. And this, of course, this makes it the maximum force buoyancy. Especially the maximum has to be greater than the weight, right? Minimum force buoyancy is 0 when you don't have anything part of it submerged, right? The maximum has to be greater than the weight is greater than rho of the object, V of the object, and G, because that is the weight, right? This is, weight is mg, that's m, mg. So it turns out two of these things cancel, the object and G, and you find rho fluid greater than rho object. So if the density of the fluid is greater than the density of the object, it will float. So you can get a relative measure of the density to figure out if something is going to float or not. That's what we saw before in the words, and that's what we see now. So let's go take a couple more looks at a few more virtual demonstrations, and we'll find them over here. Okay. The floating Coke cans. What is the density of Coke versus water?
Floating Coke cans. Will Pepsi sink? or a Coke sink, or will it float?
Now this is the regular Coke. That's got a lot of sugar in it. Now if you've ever tried taking some sugar and put it in water and dissolving it, you can put an awful lot of sugar into water. There's an awful lot of sugar in the Coke that brings the density up. Now the diet stuff, you have a little bit of
different mass. Soda has sugar, making it more dense than the diet soda, which does not.
Yeah, the diet soda has some artificial stuff which is very sweet. You don't need much of it, and so you don't get that big of a density effect. You might ask, why does the little end of the can go up instead of sitting sideways? That's because it's actually unstable, and the little air bubble in the thing will float to the corner, and that's why it floats that way. Another demonstration here is with bowling balls.
Floating bowling balls. If I place a bowling ball into the aquarium, will it sink or will it float? It'll float.
It's actually changing its density as you bubble that air out of the finger holes.
If we put a 14-pound bowling ball.
So the 10-pound bowling ball, 10-pound bowling ball floats.
It'll sink. Both bowling balls have the same volume, but as you know from bowling, they have different weights. 10-pound ball floats, the 14-pound sinks. The 12-pound bowling ball is approximately the same density as water and would just barely float.
Okay, so there you learned about bowling water and how you can tell that if you don't know what weight your ball is, you can try floating it and figure it out that way. And this one is a case when, remember how I said a fish has a little air bladder and it can change the volume of its air bladder, and that will change whether or not it goes up in the water or down? Well, this is the physicist version of that thing, right? And so it's called the Cartesian diver. And what it is if you look carefully, there's a little medicine dropper there. The black part is rubber, it's on top of a piece of glass. If you squeeze it, you squeeze the little dropper, and that makes it have less volume of air, and so the thing sinks. And if you let go, the dropper opens back up, you have less pressure on that air that's trapped inside the little medicine dropper, and it goes up. So it's just about balanced with the amount of air that's in that medicine dropper. And then as you change the density, like a fish squeezes on its air bladder to change the density, you go up and down. So if you have, you hold on to a sort of a amount of one of these air toys and get just the right amount of air in it, you can kind of get a neutral balance so you can squeeze it and sink and go up yourself. You probably have to put some weights on. Most people will float because their average density is less than that of water. If you have trouble floating, then just breathe in, and that's effectively reducing your average density, and you float higher. So if you, next time you're floating, you breathe in, you reduce the average density, you float higher, you breathe out, you sink a little bit more into the water. And so that is the end of this set of demonstrations. And that will bring us back to the camera again. So let's pop back there. And here's a little quickie quiz question. I actually promised you one of these. And here it is. You're sitting in a car strapped at a traffic light, holding the string of a helium balloon. And you light turns green, driver starts going forward. Which way does the balloon pull in the string relative to you? And commit to your answer while I'm drawing this out. I'm going to write in air over here. And air, your balloon's going up like this. And the acceleration of the car, let's say, is this way. Car plus air plus balloon. And so the air inertia is bigger than the helium. This is helium in here. And the density of helium is less than the density of air. How do you know? Because it floats, right? That's how you know. It tries to float. It's on a string, so you can't get all the way to the top. So the air inertia is greater than the helium inertia. And that means that the air tries to stay in the same place. So the air is pushed back. Needs more force to get going. And that means that this air, now that's been pushed back, forces the balloon the other way, forward. And so the balloon goes like this. It goes forward towards the front of the car because the air goes this way relative to the car. And so the balloon has to go that way to make up for it, right? The air goes that way and it's trying to float in the air, it goes the other way. So this is the answer. Now I think it's useful to say in vacuum what happens. First, what does a helium balloon do in vacuum? There's no buoyancy. Since rho vacuum equals 0. There's no density of vacuum. There's nothing there. So there's no buoyancy at all. So it hangs, the balloon doesn't float. It goes straight down in vacuum. It gets pretty big too, right? Because there's a lot of pressure in there. You need a strong balloon. Acceleration is still this way. And so this is just held back by inertia. It needs the tension in the string to give the acceleration, since inertia holds it. And so it needs the tension in the string, right? The string is push-pulling this way, so it has a component this way to give it A, and has a component this way to correct for mg. Now, if we looked over here, we'd have to talk about buoyancy and how the thing's accelerating. The apparent direction of gravity is what comes up over here. Okay, so this one is something you could do the same thing with a mass, right? This is if you accelerate and holding a mass is going to do this. Buoyancy tends to make it go the other way because it's the opposite. Air goes that way, it goes opposite. And here's a problem that's a little bit like something that you've already seen because we just calculated one of these things here. So we'll run through it quickly. What is the tension in the string? Okay, so the force of the string is going up. And that's 8 newtons. We have the force of buoyancy going up. And force of the buoyancy, wait a minute, this is suspended from the string and this is air, right? But do air first. And the weight's going down. And it's suspended, so that's static. A is equal to 0. And so in the air, this is it. F string is equal to W. So W is equal to 8 newtons. Okay, now we go into the water, where we have the same W down, doesn't change. We have a different string up, and we have the force buoyancy up. Force buoyancy is rho of the fluid, volume of the object times g. This is the volume of the brick, right? And 408 milliliters is equal to 408 decimeters cubed, and that's 40, well, each of those is a tenth of a meter, so 123.408 meters cubed. And so the sorry, wait a minute, that's 0.408 milliliters. So this is for a liter, E minus 3. So this is got a 4.08 E minus minus 3, and then another 3, it's 6, and that's 0.408 E minus 3 meters cubed, and so this is E minus 4 meter cubed. Okay, because that's milliliters, not liters. Okay, so that's our volume, and so the again, F net is equal to F string plus F buoyancy minus W is equal to MA is equal to 0. So F string is equal to W minus force buoyancy is equal to 8 newtons minus force of buoyancy is density of fluid, 1,000 kilograms per meters cubed. Volume 4.08 E minus 4 meter cubes, 9.8 meters per second squared. Okay, and 1,000 and another 10 gives us 10 to the fourth, so we should get around 4 for this, and subtract 4. So this is equal to 8 newtons minus 4 newtons equals 4 newtons, and that's this one. So that is similar to what we did with our brick. And the next thing to do is an iceberg. So an iceberg has a density of 917 kilograms per meter cubed. Ice is less dense than water. Seawater is more dense than regular water. Regular water without the salt is 1,000 kilograms per meter cubed. When you dissolve salt in it, enough to make seawater, it increases the density just a little bit. Because salt doesn't dissolve as much as sugar into the water, it's a much bigger change. What percent of the iceberg will float above the water? Well, we start this as we usually do, talking about a buoyancy force. So we'll draw a free body or force diagram. Force buoyancy is up, and that's equal to rho fluid, V below times G, and then downwards is the weight of the ice is equal to rho of ice times V of the all ice times G, and no bounce. implies A is equal to 0. So F net is equal to MA is equal to 0. And F net is equal to FB going up, and the weight of the ice going down is equal to 0. So the buoyancy equals the ice weight. If we plug in what we have written over here, it's rho water, V below, G is equal to rho ice, V total, times G. G's come out, and we get V below over V total is equal to rho ice over rho water. So this particular thing right here is the fraction below. Now, what we want is percent above. Okay, that's not what we have. So let's work this out. This is what we want is equal to the fraction above times 100%. Now 100% is equal to 1, so a unit conversion 100% divided by 1 is equal to 1. And the fraction above is, of course, 1 minus the fraction below, V below over V total, times 100%. And if we plug in this ratio here, this is 1 minus rho ice over rho water, so 100%. And if you put in ice and water from above, you get 10.5%. So that is the percent of the iceberg above water. So this compared to that. 10% above, 90% below. The tip of the iceberg, right, is 10% if you go and calculate it out all the way. Now, at this point, it's useful to, I guess, show you some more travel pictures, right? Doesn't that make sense? Okay, so let's do it. There's, go. There's a nice travel picture. This one's from the Great Salt Lake. And, you know, the Great Salt Lake is, to get enough salt in it, that when you get it on your skin, if you're going to go swimming in it, which is kind of neat because you float high because the density is higher, if it's got enough salt in it, they'll irritate your skin if it stays on it for too long. When it starts drying, it's too salty. So you want to wash off with fresh water. So of course you bring along your gallon of fresh water with you to wash out for, and the natural thing to do is to toss it into the water and see it float, because you can see water floating on water, and that's kind of neat. So you do that, and it looks to me you've got about a quarter of that fresh water gallon is sticking out of the water. And I kind of took a gallon and leveled it off and saw how much water you had to take out to get it to match up with the water surface, and that's where you come up with about the quarter. The other interesting thing here is if you look over on the sides, you notice that nice circular waves coming from the wave source here in the middle. And in the notice here, you see how this back there's low spots going off that way and here. That is your interference that we saw the other day. So we can see lots of things in this picture. But what we're here really now is just think about this particular water. So let's flip this over and say Great Salt Lake ice density. And so let's begin. Here we have our, from the picture, about 1/4 of the fresh water is above the surface. When it floats in the Great Salt Lake. And Great Salt Lake is pretty close to near saturated salt solution. I can tell that because there's lots of salt that's kind of depositing out as the air dries the water. You get these salt deposits on the shore, and the water's right up against them. So you know it's really close to saturated. Maybe just after it rains, it's not for a little while, but I don't think it had rained in a while. So it's really pretty close to saturated. You can actually look it up and get the density, because I didn't do that. But what we did learn from the last anyway, we don't know what is rho Great Salt Lake. Okay, so from the iceberg problem, we can use this. We have V below over V total is equal to rho, in this case, the stuff that's floating, which is the fresh water, over rho Great Salt Lake. And this, okay, as 1/4 is above, that means 3/4 is below. So this is 0.75, right? And this here is 1,000 kilograms per meter cubed. So rho Great Salt Lake is equal to 0.75. Wait a minute, that's the other way around. This goes up, that goes down. It equals to rho freshwater over the 0.75, which is 1,000 kilograms per meter cubed over 3/4. And so that's 4/3. So you get 4,000 divided by 3, which is 1,333, right? Something like that. And so that is about what the density of the Great Salt Lake is. Saturated salt solution is not too far off from that. And probably, again, it's the error in this fraction, the measured fraction, that if we worked hard to get that right on, then we're going to be able to solve that. So let's then go back to the PowerPoint. And our PowerPoint, what happened to our PowerPoint? This one here. Okay, so here's our PowerPoint, and front of the car, and we did the 4, and we did the 10.5%. Here's a bunch of questions for you. Fluids always exert force and pressure perpendicular to a surface. And the answer is, really what we mean here is static fluids. The answer is true. And that the force is delta P times A. Pressure is the same at any 2 points in an open container at the same depth, regardless of the shape of the container. Yes, we had a demo that showed that. Level of fluid is the same everywhere in an open container, regardless of the shape of the container. Neglecting capillary effects. Yes, there's a demo for that. 4, if the pressure at a static fluid increases by delta P, it also increases in another place. This is a statement of Pascal's principle. That's true. The buoyant force of an object is equal to the weight of the fluid of that object displaces. Think about that. Force is the weight of the fluid. Well, weight is a force, and weight of the fluid that displaces is the volume of the object times the density of the fluids. That's true. That's Archimedes' principle. Number 6, the buoyant force on an object is equal to the difference between upward and downward fluid forces on it. Yeah, that's right. That's a different way of putting it when you're analyzing the force, as you would to derive pressure versus depth, which we kind of did ourselves, not as well as we could have. An object or a fluid with a density smaller than the surrounding fluid will float upwards. Yes, you need a fluid if you're going to have a if you're going to have this work, but that's fine. And that's the end of that. Okay, and so let's pop over to here, and I'll put this up with my comments on it. So if you have static fluids, the force is this, that's what it is. And we had demonstrated with these two. This one you had to neglect the capillary effects. We have Pascal's principle and Archimedes' principle. And this one here is a little free body-ish type diagram. It's the same on the sides at any given height, all the way up and down. They don't matter. On the top, you have the pressure at the top, and the bottom, you have the pressure at the bottom. Right? There's a difference in pressure from the height, and that is the buoyant force. Now, if you have a weird shaped object, that's kind of hard to see, but that's the case. So if you have a fluid whose density is smaller, an object is easy to see. But if you have a fluid whose density is small, you have to have a surface. So you have to have fluids that don't mix with each other, like oil and water. That gives you a surface because they don't mix. If it's alcohol and water, it may have a different density, but they just mix together, so you don't see anything. But if it's oil and water, they don't mix, and so there's a surface between them, and the surfaces get pushed by a pressure force, and that's why oil floats on water, because you get that thing to mix. But alcohols just mix together. Okay, that is the end of static fluids. Next time we come back will be 12A, which is optional this semester, but is about fluid dynamics. Okay, so that's it. Let me get us out of here.